I think we all know that if I take this metal ring and I move it like this, it has kinetic energy, 1/2 mv squared. But what if I put it on this turntable and I give it a spin? It's not going anywhere. But does it have kinetic energy? Every particle is moving. It has rotational kinetic energy. If we have a mass moving with a velocity, we say it has a kinetic energy equal to 1/2 mv squared. Well, that's the linear kinetic energy. What if we mounted the mass on a rod of radius r and we had it rotate at omega? Since we know omega times r equals v, we can convert the linear kinetic energy into angular terms. We have 1/2 m omega squared r squared. Something in there looks familiar. Do you recognize mr squared? All the mass is at the full radius. That is the rotational inertia. So here we have the kinetic energy, rotational. It's the same amount of kinetic energy if we express it linearly or rotationally. Let's test that idea with some numbers. Let's say the mass is 5 kilograms and it's moving 3 meters per second tangentially. And we have a radius of 1.5 meters. Using that radius and that velocity, we'll get 2 radians per second for the omega. Kinetic energy linear, 1/2 mv squared. Plug in the numbers. We get 22.5 joules. Let's try it in rotational terms. Let's find out what the rotational inertia is. Plug in the values, and we have 11.25 kilogram meters squared. Plug in I and omega, and yeah, we get 22.5 joules. It better be the same. It's only one object, so however we look at it, it has the same kinetic energy. So here's a good problem to practice. Let's say we take a ring with 3.5 kilograms with a radius of 10 centimeters. And let's say I put it on a massless turntable and I apply a force tangentially of 4 newtons through an angle of 1 rotation. Why don't you try to figure out how much work did I do? And I want you to use rotational terms. Then ask yourself, how much kinetic energy did the ring gain? Then you can find the final omega. Now pause the video and go try this before I do it. Well, we know that work is a force times a distance parallel, which is equivalent to saying torque times an angle. And that angle would have to be in radians. The torque is a force times a radius. We can plug in the data and we have 2 pi radians for 1 rotation. And we get 2.513 joules. Okay, that takes care of A. Of course, you can see that this is the same thing as taking a force times the distance. So what happened to the work that I did? It went into making this thing rotate faster and faster. How much kinetic energy did the ring gain? It had to gain that much kinetic energy. It did not go uphill. We're not talking about any waste heat here. And we can think of this as rotational kinetic energy. If the change in kinetic energy is the KE final minus the KE initial, this must be the final KE because we don't have an initial angular velocity. Using the formula for rotational kinetic energy, we can calculate the omega final. Since it's a ring, the rotational inertia is mr squared. All the mass is at the full radius. Plugging in all the data, and we get 11.98 radians per second for the omega final. So you might be wondering, if we have a ring and it has an omega, couldn't we say all the mass has the same tangential velocity? And then just use linear kinetic energy? Yeah, that'll work for a ring. But what about a disk? Does all the mass have the same tangential velocity? Not at all. The mass is distributed along this radius, with diminishing tangential velocities as we approach the center. And this is a good reason to use rotational kinetic energy. The entire mass has the same angular velocity. So in the last problem, if we used a disk instead of a ring, we would just have to change the rotational inertia to 1/2 mr squared instead of mr squared. Well, could we have a situation where we have both linear and rotational kinetic energy? I have rotational kinetic energy. I have linear kinetic energy. I could do both. Whenever you see an object rolling, it has both linear and rotational kinetic energy. So let's say we have a disk of mass m and radius r. It's rolling along the floor at velocity v. Can you find the KE? Yeah, pause the video. Try it first. Does it have linear kinetic energy? That was easy. Does it have rotational kinetic energy? Yeah, 1/2 I omega squared. But how do we add them up? The total kinetic energy is the kinetic energy linear plus the kinetic energy rotational. Now we just have to get some common terms here. We can put in the inertia, 1/2 mr squared for I. And since we know omega times r equals v, we can put in v squared over r squared for omega squared. Anybody see what's going to happen with the radius? How about 1/2 times 1/2? Now we're getting somewhere. And there's your total kinetic energy. So this is the amount of energy due to the object moving forward. This is the amount of energy due to the object rotating. Well, here's a good practice problem. How about we have a disc, radius 15 centimeters, mass 3 kilograms, and is rolling along the floor at 2.1 meters per second. It encounters an incline. How high up will it go? Yeah, pause the video and try it yourself. Conservation of energy. We're going to have both kinds of kinetic energy on the initial side. At the end, we've come to a stop. We only have potential energy, gravitational. Rather than just plug a bunch of numbers in, you ought to practice writing these formulas down. Yep, it's just like what we showed you. Practice, practice, practice. 3/4 mv squared. And what about that gravitational potential energy? mgh final. Well, this works out to be 9.9 joules of kinetic energy. It's being converted into 9.9 joules of gravitational potential energy. Do the math, you get 0.3375 meters for the height final. Of course, if you wanted to, you didn't have to calculate the energy. You could cancel the mass, divide by g, and get the h final. Would you get the same answer if that was a ring or a sphere? Nah, you have to change the inertia in the formula. Now, we're going to do a lab later where we're going to roll a ball, a disc, and a ring down the ramp, and you can use conservation of energy to calculate the final velocity. Try deriving a theoretical formula for the final velocity.